Welcome everyone to today's webinar, Tecnoflon Low Temperature FKMs, Benefits versus Common Elastomers. We're very excited to have you here with us for this episode of our Researcher Live series. We're thrilled to bring on experts and thought leaders from around the world to discuss topics that can benefit and inform your research. On today's Researcher Live episode, we're diving into a topic of great importance for anyone facing critical applications with extreme temperatures, fluoroelastomers. We'll discuss what sets FKMs apart from common elastomers and explore the benefits they offer in harsh environments. Before I officially present our expert panelists today, just a couple of housekeeping items. You're all in listening mode, so you don't have to worry about any background noise. If you have to jump earlier, no worries at all. We'll be sending out the recording to you. And to ask a question in the Zoom bar below, you see where it says Q&A. So just click on that and you can add your questions as they come up. Depending on the question, we'll have dedicated time at the end of the webinar. Or if it's like more of a clarifying question at the moment, we'll add it then. But yeah, make sure to add all of your questions as they come up so you don't lose track of them. And then we'll make sure to cover them all. Now, welcome to today's presenter and thought leader joining us, Nicola Ranieri. Nicola was born in Lucca, Tuscany, and holds both a master's degree in industrial chemistry from the University of Pisa, as well as a PhD in polymer chemistry from the Max Planck Institute in Mainz, Germany. Nicola has been working in the field of elastomers since 2001, having specialized in VAE elastomers at Wacker in Germany, and silicone RTV at Blue Star before landing a role with Solvay in 2013. During his time at Solvay, Nicola has developed fluoro and perfluoroelastomers to support various industries, including automotive, semiconductor, oil and gas, and chemical manufacturing. Welcome to our Researcher Live webinar, Nicola. My name is Julia. Great to have you here. My name is Julia Heeson. I'm a Senior Growth Marketing Manager at Research Solutions, and I'll be your moderator for today. Before I officially hand it over, just a couple of sentences about the company behind Researcher Live. Research Solutions was founded in 2006 and provides solutions that simplify and streamline how organizations discover, acquire, and manage scientific articles and data. More than 70% of the world's top pharmaceutical companies, emerging life science firms, and other R&D-driven companies rely on us for one-click access to scientific literature. Before I now really hand it over to you, Nicola, we would love to know a bit about you today, our audience. So I'm going to pull up a poll as we speak right now. Let me pull this up, and we would love to know what industry you're in, get to know you a little bit better. Okay, so you should all be able to see the question. So just add the industry that you're in today. Okay, see some people already filling in their options. Give you another second here. Okay. Got a handful of people filling this out. Okay, let me share the results here. Okay, looks like people in maybe the North American time zone, it's a little early for us. I feel like some haven't filled this out, but as we see, we got quite a lot in the chemical industry. So that's interesting. And of course, if your industry wasn't mentioned here, feel free to add that in the chat. We would love to know. Okay, now I officially do hand it over to you, Nicola.
Welcome and good afternoon, but also good morning, good evening. So today I will try to explain how low temperature elastomers work in a cold and aggressive environment and how fluoroelastomers can serve this kind of applications. Let me browse. The tools that I will use and will explain during this presentation are both techniques common for all polymers, but also some that are specific for elastomers, such as the compression set, the temperature of retraction test, the dynamic mechanical analysis. But before going into these details and also to see what are elastomers, what are rubbers, which kind of elastomers were analyzed and characterized in this study, let me spend just one word about Solvay, the company I have joined in 2013. Don't know if I can switch. Yes. So I've joined Solvay Group, and more specifically it's Solvay Materials Group that is specialized in specialty polymers, that are polymers at the edge of the pyramid. That the famous pyramid of performance is the one that describes the polymers according to their thermal and chemical resistance. And at the top, you find only very special materials that serve as the ultimate solution when other common materials have reached their limit. For example, among aromatic polymers, we produce polyether ketones, polyamidamides, polyphenyl sulfide, and the like. Among fluoroelastomers, PVDF is probably the most known because it's used in electrical batteries, but the topic of today will be around fluoroelastomers, FKMs. These materials have the broadest combination of resistance to chemicals and to temperature. That's why they are the answer that where nothing else, the difference between an elastomer and a rubber. So the elastomer is a polymer with very high flexibility, very high mobility. So that is the ability to recover from any kind of deformation without rupture. But this kind of flexibility can be measured in a way by the glass transition temperature, TG. This is a temperature common for any polymers, and the lower this temperature, the higher the mobility of the polymer. So the higher the difference between this temperature, this glass transition temperature, and the surface temperature at which the elastomer is applied, the higher the flexibility and the higher the elasticity itself of the rubber. Indeed, a rubber is made of elastomer. A rubber is made of vulcanized or cross-linked or cured elastomer chains. The words are different, but the meaning is the same. The vulcanization is the way to chemically link different elastomer chains together. And this vulcanization is key for a rubber. Without that, any elastomer is like a chewing gum. Whatever the deformation, it is not recovered. Instead, by anchoring all these kind of spaghetti, as you see in this very Italian example on the bottom of the slide, by anchoring these different chains together, you give them anchoring point so that once stressed, stretched, or compressed, once the stress is removed, these chains, these spaghetti-like chains, can come together back to the original shape. And that is the key property of rubbers, the way to tolerate any deformation without rupture. That's why we can see a lot of their application in everyday life. Let's see if we move forward. Yes. So another very Italian example is the coffee mocha machine, where there is a gasket, but many other, let's say, everyday objects have a rubber part, a sealing element in it. This is because these sealing parts, these rubber parts, are the ones that compensate any kind of irregularity of any kind of surface. Usually the most common is metal. Two metal parts, like two flanges that have to be joined together. There, where it needs to be defect-free, there is a rubber part, a rubber gasket. And this rubber gasket that is compressed between the two metal surfaces in this example provide also an elastic force that keeps the two joint parts tight together. So this is a key property of any equipment. Any part, any moving part or static part in service has a rubber element in it, because it is the door between the service environment where the core of the part takes place, its life takes place, and the outdoor environment. So it is a protecting element. I like this image of the, even if it is an unfortunate event of the Challenger disaster in 1986, because it speaks more than diagrams than figures about the importance of a simple part such as a small O-ring. In that case, it was this kind of O-ring that is really, I don't know if you've ever seen that, is an O-shaped ring made of rubber that provides the simplest service as a sealing part. In that example, there was a bad design of that kind of O-ring, and even if it was very small part in such a big shuttle, it was the reason why it failed. Indeed, since we are talking about fluoroelastomers that are at the edge of the performance, we are now talking about very demanding applications. So applications where the sealing part has to resist to heat, so high temperatures, to a very aggressive chemical environment, to also the ability to serve at very low temperatures, so exposure to extreme temperature, very high, very low, and to provide also kind of abrasion resistance, mechanical resistance. So ideally, the best design sealing element will be fulfilling all the four main requirements altogether. When this is true, the service life of the part is the longest possible, and this is a way to have not only the highest safety degree, because as we said, the sealing part is the door between the service environment and the outside, but also in terms of cost, because if the service life is the longest, even the maintenance cycles is the longest. And this is, of course, cost saving for the industry, whatever industry we are talking about.
I was on mute. Yes. Got another question there for you, everyone. Let me see and get back here. Okay, Zoom is not on our side today, but doesn't matter. I will pull this up here. Now, we would really like to know, talking about challenges, what challenges do you face working with elastomers? And there are, of course, like 7-8 options that we have here. If that is temperature flexibility, thermal resistance, mechanical stresses, harsh environments, surface properties, weight, exposure to chemicals, all of the above, or if it's something totally different, again, feel free to add that in the chat. So we'll just like take a moment here. Fill in your options. Okay, awesome, interesting. One more moment if you haven't added yours yet. Okay, let's see the results, sharing them right now. Interesting.
It's it's a common set of let's say challenges, especially when we talk about not common elastomers, not the ones that we see, for example, in the coffee machine. And especially in the chemical industry, what we are asked to provide is a part that works at cold temperatures, where temperature flexibility is a key, but also the ability to maintain this flexibility under thermal stress and in harsh environments, where with harsh, we generally define a combination of chemicals that can really react with the elastomer. And the study was focused exactly on these requirements, trying to see what happens at an elastomer. When we try to assess this study, we were thinking of how to have a model of a rubber. So we can think of a rubber like a ladder, where the rods of the ladder are the elastomer chains, and the steps are the vulcanization segments. So what keeps the ladder together. all these, what you see here, what an elastomer can face is exactly what you have described in the pool. And when the elastomer is subjected in his life, in the service life, to all of this all at the same time, this can result in a failure of the rubber part itself. And generally, when we take the example of the ladder, there are the three main paths that can lead to the failure during service. One is the chemical degradation, a chemical that attacks really the polymer, the elastomer chain that is the constituent of the rubber. Both can be the vulcanization or the links or the polymer itself. In any case, what we observe is that the material fails dramatically in terms of mechanical performance. Another scenario can be the famous heat hardening. I say famous because it's something that we can experience also in our daily life with the elastic bands. I think most of you have seen that exposing elastic bands to sunlight or to heat for some period of time will translate into this band to become brittle and powdery, so it breaks just by touching. Same happens also with all elastomers, also with the most performing. When heat is too much, there are additional cross-linking points, additional vulcanization segments that are formed, and this causes the elastomer to become brittle as glass, heat hardening. Even in this case, we lose the main feature of the rubber, its elasticity. Something again to be avoided. Another kind of, instead of reversible failure, is welding by solvents. In this case, the mechanical properties become weaker, but they are recovered back to the original state once that this solvent has volatilized off, is removed. In any case, our study was to focus on what happens to the cold flexibility. Is the service close to the limit of that is the TG of the polymer kept during the service, or is it affected by these scenarios, by these challenges offered by chemical or heat failure? And the object of our studies was polymers taken in the edge of the performance. So the graph that we have seen before, the ASTM classification, these are the polymers of that graph. We are not talking about natural rubber or more common elastomers. We are talking about elastomers that serve at least up to 150 degrees C in the service, and that resist to more severe chemicals than water or water-based solution, for example. So HMBR, acrylic elastomers, epichlorohydrin-based elastomers, silicon, fluorosilicon, and fluoroelastomer based on Tecnoflon technology, both PL, but especially VPL, that are elastomers made by a proprietary constituent block called monomer developed by Solvay that combines not only cold flexibility, but also excellent chemical stability, that are properties that are expected actually by a fluoroelastomer polymer, because as we have seen, this is at the edge of the performance. And this is a very simplified scheme of how these polymers are made. And my point was to describe the intrinsic property of VPL fluoroelastomer, that is indeed the carbon-fluorine bond. So we are really talking chemistry now. And the energy of these bonds, of the carbon-fluorine bond, so how much is required to thermally destroy this bond, and so to destroy the polymer itself, is the highest energy in the organic chemistry. This table shows that actually there is this silicon-oxygen bond that is a little bit higher than our carbon-fluorine bond, but this is formally belonging to another word, an organic chemistry, like silica stones. So thermally, the fluorine chemistry is the most resistant, but not only chemically, not only thermally, but also chemically. And I show you a picture here that this is the ASTM T2000 graph. Sorry, the picture comes later and it speaks better than this graph. This graph is an official ranking based on reference oil, the IRM 903. So and on the thermal rating, so exposing the elastomers to different temperatures until they fail. This is a way to position technically different elastomers. And the lower the swelling in the reference oil, the higher the chemical resistance. So in this part, we have the best performing polymers. And as you can see, FKM at the edge, there is only one class that is even better than the fluoroelastomers. And this is the perfluoroelastomer class that has an even higher content of carbon-fluorine bonds. So you see the fluorosilicon, HMDR, silicon, they're all represented here in the high performance chart according to the ASTM D2000. Now, this was the picture that I like better than this representation, because it's a simple experiment that everybody can do, and that shows very quick how chemical resistance translates into a real application. We have made the same O-ring based on HMDR rubber, on silicone, and on our Tecnoflon VPL FKM, so fluoroelastomer. And we have immersed the 3 samples in toluene for 1 day at room temperature. The next day, we observed how much this swelling, the chemical resistance looked like. So the swelling means volume increase. That means that the toluene could enter, could diffuse into the O-ring. And you see that in this case, HMDR and silicon also, the swelling was so dramatic that they could not fit the groove anymore. So if you think of that happening only after 1 day, let's say, of service at room temperature and with a quite common solvent, you can imagine how important it is to design the right rubber to make an O-ring or a sealing part when facing more severe conditions. Indeed, this was quite a simple test for Tecnoflon that shows no difference at all after the immersion in toluene. That's why, for example, the fluoroelastomers are used in contact with fuels in vehicles, with kerosene, with diesel, with gasoline, whatever. And let's see what happens first at high temperatures when benchmarking elastomers. This compression set test is very common in the rubber world. You can find this figure in all the technical documents of each of these elastomers. So what we do is usually taking a reference specimen, can be an O-ring or a button shape, and this specimen is compressed of 25 its original geometry, 25%. It is kept with this compression rate for usually 70 hours at 200 degrees C. And after this period of time, the compression is removed and the elastomer specimen is left free to recover its original shape. The compression set is defined as the percentage of this 25% compression that is left over after the removal of the compression. So you expect that the best elastomer is the one with 0% compression set. So the ability to recover everything of the original shape. And the lower the compression set number, the better the performance. In this graph, I have reported the test made at 200 degrees C for 70 hours for not only the fluoroelastomer and VPL grade or the other VPL that is the best in class for temperature, for cold and heat temperature together, but also some of the best performing reference for high temperature application, that is fluorosilicon, silicon, acrylic rubber, HMDR, and acrylic rubber with even better composition to resist to 200 degrees C. You see that easily the fluoroelastomers are the ones with the best performance. And indeed, many of these polymers, HMDR, for example, are already at their limit at 200 degrees C. This is not only a test for the laboratory, but the compression set happens also in real life, like in this picture that is a part of a cooling system or a vehicle cooling system. So the elastomer is subjected to high temperatures. And in this case, the rubber was based on APDM polymer. And probably in that case, the temperature exceeded the design of the part. It exceeded at 130 degrees C, that is the max temperature for APDM polymer. And I don't know if you can see well, but in that case, instead of a circular shape, the sealing, the gasket is flattened, so it doesn't have any of the original shape anymore. Compression set is 100%. It is the part was failing in service. So compression set is a way to anticipate what can happen in service. But now we said at the beginning that we wanted to focus on cold temperature. So what happens when the elastomer is applied close to its TG? So this, I repeat, this is the temperature at which above which the elastomer is elastic, able to tolerate deformations, and below which it turns to be glass, iced, frozen. So first question is the temperature, the TG, independent from the external pressure? The answer is no. The literature teaches that every polymer shifts its TG upwards when the pressure increases. And this graph was done in Solvay many years ago, and it demonstrates that this is, of course, happening also with fluoroelastomers, like our VPL 55540, with a nominal TG of -40, -39 in this case. And in this, with this technology, we have seen that more or less every 100 bar or the additional pressure, the TG increases of 3 degrees C. It doesn't look so significant, but if you think about subsea applications, for example, we have some application at 3,000 meter of depth. So depth translates into 300 bars of pressure. And in that case, the nominal TG of the elastomer shifts 10 degrees, more or less, upwards. So the water temperature there is 4 degrees plus. Usually, if you don't think about the shift, you say that an elastomer with TG of -10 can serve very well if the service temperature is 4. But at 300 pressure or bar of pressure or additional pressure, its TG has moved to 0, too close to the water temperature of 4. You have to take, by design, a nominal TG, like in this case, -39. You are sure that with that shift, you are still in a safe range. Still having the same package of good properties of chemical resistance, of heat resistance that is typical of fluoroelastomers. So another point of attention when designing the right part of elastomer is to know the external pressure, because this can drive already by design the choice of the elastomer, can reduce the number of polymers among which one can choose the right one. The compression the compression set experiment to assess the sealing ability can be done also at cold temperatures. This test is the same. The specimen is still compressed 25% of its original dimension, but this time it is frozen instead of submitted to very high temperatures. It is frozen. In this case, we chose -40 degrees C, so an Arctic condition, to see what happens at these polymers that are the ones with the lowest TG available in the market. After 1 hour of conditioning, the compression is removed and the elastomer is left free to move to recover its original dimension, still at -40 degrees C. And what we have measured is how much of the original shape is recovered after 1 minute after the removal of the compression, after 10 minutes, and after 1 hour, that is the final recovery of the dimension. And we can see in this graph, using again the VPL with the TG of -40, the last 2 digits are the TG in our nomenclature, compared to elastomer whose nominal TG is much lower, like silicone or fluorosilicone, and with polymers whose TG is -30, so above this -40 temperature of the test. This graph confirms what people expect, that the DSC, so the analytical method to assess the TG, is already giving you the answer before doing this test. The compression set is driven by TG of the polymer. You don't expect that the polymer whose TG is -30, so it's frozen below -30. You don't expect this polymer to perform like an elastomer when you measure it, when you test it at -40. And this is explained better, maybe in this kind of graph, where we have put the compression set observed in the experiment before, we have correlated that with the TG of the elastomer of each of these specimens. You see that the best performance, so the lowest compression set, is achieved when the TG of the polymer is below the test temperature, in this case, -40. This is a really static test. There is nothing else that cold there. There is only a fridge to make this, but this is not actually the real life, because we have seen so far the elastomers are in a dynamic environment, not only dynamic in the term of mechanical stress, but dynamic because temperature can change, can switch from high to low and vice versa, and chemical spray roll as well. So we wanted to see what happens when the elastomer is subjected to all of this. What happens to its ability to serve at such low temperatures? Is the chemical resistance affecting the ability to seal at low temperature? Is the heat resistance also affecting its, at the end, its TG, its, the ability to be elastic still at -40, because this is the challenge. To investigate this behavior, we have chosen the temperature of retraction test, the TR test. This is very common in the rubber world. And the test procedure is quite simple. We take a vulcanized specimen, a dog bone-like specimen, and we stretch this specimen of 50% of its original dimension. Then, with the stretching still in place, we freeze that specimen well below its TG, -70°C, -60°C, so we are sure that it's frozen. And we remove, at that point, we remove one of the clamps. We leave the polymer free to recover the original shape. Indeed, the heating is started, and we see at which temperature 10% of the original shape is recovered. And it is the well-known TR10 temperature in the rubber world that is used instead of TG, more or less with the same value. Then the measurement goes on, the heating proceeds, and we record the temperature at which 30% of the original shape is recovered, the 50% and the 70%. So with these 4 points, we build this kind of temperature of retraction curve. And the steeper the curve, we say the more ideal the elastic behavior. So what is expected is that the elastomer, the rubber, behaves like a switch at the TG. It's not the case because polymers are not ideal materials. So we expect anyway that to have a steep curve, and most important, that this curve does not change during the service life. That what we design to work is still working during all the service life expected for the part. Is this the case? We recorded this curve before a chemical exposure or before a heat exposure. And what is exemplified here is the question mark. Is that happening? Is the curve changing shape after the test? We started with a chemical resistance test. So we have measured this temperature retraction test for selected elastomers. So our VPL elastomer with TG -45, that is still experimental and has a limited use so far. And with another most common grade, the PL455 with a TG around -30. Comparing with fluorosilicon, with acrylic rubbers, AIM, and with HMBR, with high acrylonitrile content, that is usually a way to address the best chemical resistance of the HMBR rubbers. The test was done by taking the samples and immersing them for 1 week at 100°C in fuel C, that is an hydrocarbon mix very common in the automotive industry, added of 1% of benzylamine. This was chosen as a simulant, as a reference fluid for engine oils, for transmission oils, where beside the paraffinic part, the hydrocarbon part, there is always an anti-corrosion or anti-inhibition additive based on amine chemistry. And amines are usually aggressive for almost all the elastomers, not only silicones or acrylic rubbers, but usually also for fluoroelastomers. The same curve. So the temperature retraction curve was measured after this exposure. And you see here, dry out at 150 was needed to remove after the test all the residual fuel and benzylamine to test the real elastomer after the aging, not a swollen elastomer. So if we look at the blue and the light green curves, the dotted lines are the curve measured after the test. You see that there is no difference. You cannot even recognize the curve before or after the test. This is not the case starting from fluorosilicon, the orange curve. Even if not dramatic, we see a shift. The dotted line is shifted towards higher temperature, meaning that something happened during the immersion that made a rubber stiffer when compared to the original state. So to recover elasticity, one needs to warm the rubber at higher temperature than in the original state. This shift even more significant taking the acrylic rubbers EM, the green curves. You see that we have a shift of almost 8 to 10 degrees C. That means that after this immersion, the elastomer part is not able to seal anymore at -30. It is in its glassy state. We have really shifted the nominal TG to higher values. So in that case, this rubber would not be serving anymore in this environment at these cold temperatures. Even worse when we talk about HMBR. This grade was probably not the best one for this experiment, either for the temperature or for the environment. But after the test, the specimen was not recovered, it was destroyed, so we could not measure the temperature retraction curve anymore. So this is an example where fluoroelastomer provide a solution being not attacked by this kind of chemical set. We wanted to test the same at high temperature. So we chose a temperature of 200 degrees C that is okay for fluoroelastomer, but can be a challenge already for silicon-based rubbers like silicon BMQ or fluorosilicon FBMQ. Also, we wanted to have in the same test, again, the acrylic rubbers, because they are at the next best alternative to silicones and to fluoroelastomers. So we exposed the same TR specimen, temperature retraction specimen, to 200 degrees C in an oven for 1 week. And after that exposure, we measured this retraction test compared to the original curve again. And if we look at hardness change, that is a simple measurement that everyone can perform. That is a simple way and quick way to assess the resistance to temperature. The higher the hardness change, the worse the performance. In this case, yes, we have an indication that acrylic rubber is not performing very well compared to VPL fluoroelastomer or to fluoroelastomer. But then we cannot see anything about cold service. We need to go to the temperature retraction test. And indeed, here we have some interesting information. The acrylic elastomer, the green one, is, yes, we have seen already in the hardness test, there is something happening. Even in this case, the dotted line is shifted upwards to higher temperatures. Something has happened that hardened the material. Maybe additional cross-links. This is a real case of heat hardening. But also, again, the fluorosilicon that should work still at 200. We see some sign of degradation because the dotted line is also moved to warmer temperature. We need higher temperature to recover elasticity. So question mark about applying this elastomer close to its nominal TG. Silicon is a very special case because not everybody knows that silicon has a TG of minus 100 degrees C, but has also a crystallization point close to -40. So this is the reason why this curve is so particular. So it's really a line. This is a crystallization in the original state. After the test, after exposure to 200 degrees C, we see that there is something that changes probably the crystallization. Even in this case, there is something that has damage the polymer chains, and that affects the crystallization temperature. So even in this temperature, in this case of silicon, this was not easy. This test was not easy for the polymer. And of course, the VPL, we have seen that the carbon-fluorine bond is very strong, and this is a confirmation again. Heat resistance is there. 1 week at 200 does not change the temperature of retraction. That means it does not change the ability of the elastomer to recover elasticity fully as in the original state. Another test, this test was borrowed by, let's say, common polymer analysis, because dynamic mechanical analysis is quite a common way to investigate polymers. In our case, we wanted to see the storage or elastic modules, as you want to call it. We wanted to see how that changes as function of the chemical resistance. And we took, again, a VPL with a glass transition at -30 compared to an acrylic sample, also with high chemical resistance, and with TG close to our material, to our VPL, -30. And the chemical resistance test was performed in an automotive fluid, an automatic transmission lubricant fluid, aging the specimen for 96 hours at 150 degrees C in this fluid, followed again by a dry out step to remove any residual fluid to be able to perform the test. Usually, what we do is, even here, is a quick assessment. We measure the mechanical properties such as tensile strength, elongation and break, hardness soon after the test. If we look at these numbers, both materials pass the test, we can say, because no significant change has occurred. But again, this does not say anything about the ability to seal close to the TG, so close to -30. We wanted to see with this DMA test what happens in the dynamic environment, because DMA is a kind of dynamic test. The specimen is oscillated with a given frequency, and this oscillation is monitored along all the temperatures from the glassy state, very cold temperature, to the rubbery state, high temperature up beyond the TG. You can see this is a transition state. This is where we want to see, is there anything changing? For the VPL, the dotted line, that is the test after the immersion in the fluid, looks the same. The transition did not move. We can safely say that it can serve as in the nominal state, like the TG is preserved. Instead, as observed for the TR test, even in the DMA analysis, the elastic modulus of the acrylic rubber is moved upwards. Even in this case, we can see that this dynamic kind of test points out that there is something happening driven by this chemical, this fluid that makes the elastomer, the acrylic rubber, more rigid, and so needing more temperature, more heat to recover the original elasticity, to perform as per design, per original design. I would like to conclude by giving you a real case example that for me was quite interesting, because it was connecting the dots between the laboratory test with the real life. And this case deals with in heat exchange and oil filtration module in an automotive, from an automotive application. It was a very famous car manufacturer that experienced some leakage from this kind of module, some oil leakage during the rest phase of the vehicle, so in the garage and in North American countries where temperatures were close to -30 degrees C. Indeed, the temperature requirement for that rubber part, for the sealing of this module, was required to be between -40, the cold service, up to -35, sorry, plus 135, peak of 150 degrees C during service. So a wide service range was required. And beside the temperature requirements, chemical resistance to both engine oils and to coolant liquid, because this module in this model, the design was so specific that the gasket had to resist both chemistry, the oil that is hydrocarbon based and the coolant that is water based. The material in use was HNDR with a low content of this ACN, that is acrylonitrile monomer. It is a way to compromise between either low temperature service or chemical resistance. In this case, the low content was chosen probably to have better cold flexibility, compromising on the chemical resistance. Indeed, what happened was that the chemical resistance was too low. The engine oil and the high temperature was attacking the HNBR gasket, leading to a failure. So there was a compression set, high compression set. When the temperature cooled down in the garage, the elastomer was not able to recover back the original function, was not able to seal as per design, and so the oil was leaking. So since this car manufacturer was quite famous and had a name to defend, they withdraw all these vehicles and ask for the best solution to seal at very low temperatures, up to -40, and with no problems at all of chemical resistance, whatever the chemical base, be that hydrocarbon based or water based. So VPL solution was the one to provide the answer to this car manufacturer, because the fluoroelastomer based on this technology, on this VPL, had exactly the same, the right combination of properties that this car manufacturer was looking for. Even if, honestly, the price range is different, because the Tecnoflon FKMs provide really the ultimate solution, this was not a problem at all, because what they were looking for was performance and the possibility to sell a solution in a very fast way and in a very comprehensive way, with no compromise at all. And all these properties that were required for this oil filter module were assessed before in the lab by doing the temperature of retraction test, the heat aging, the chemical aging. So we were able to demonstrate first in the lab what was then the reality once applied in real life. I will not be so long in the conclusion, because we have stressed a lot how the fluoroelastomer offer the best set of properties because of their chemistry, because of how the polymer is made. I wanted just to show you here this monomer. So the most important building block of the Tecnoflon VPL fluoroelastomers. Thanks to this monomer, thanks to this building block, that we can provide cold flexibility well below -30°C. That was the limit before introducing this monomer to the market, thanks to this proprietary patent of Solvay, and chemical resistance at the same time. So that is the sealing range of temperature offered by VPLs, -40 to +230. I have added also this experimental range, because we have prototypes that goes down to -55, but still not so much of demand from the market. So they are waiting for their time, their success story. Thank you. I hope I was not too fast, and you could understand my Italian English with not so much of difficulties.
Perfectly. Yes, thank you so much, Nicola. I see we've got quite a lot of questions from the audience. So before I dive into the questions, for the ones of you that aren't customers yet, and you're looking to access journal articles and book chapters quickly and effectively, I'd like to encourage you to go ahead and request a free trial with our product, Article Galaxy. And you can learn how to get up to 28% off your article spend and 86% of articles delivered within seconds. So feel free to go ahead, type in researchsolutions.com/sales and ask for that 14-day free trial. Okay, let me stop sharing my screen and let's dive right into the questions. Okay, the first question is, what about sealing performance for hot caustic soda, for example, in plate heat exchangers?
Yes, for this there are two solutions. One is a cost compromise one, and we know that caustic soda is very aggressive for fluoroelastomers. So you have to increase the fluorine content of the polymer. There are several options in the portfolio. For example, VPLs are quite okay because their fluorine content is relatively high in the portfolio. So you can still keep cold flexibility and chemical resistance. Then it depends on the temperature and the concentration of soda. If that is not enough, we have to move to perfluoroelastomers that are really the top of the top, and there's almost nothing that can destroy them. So the answer is first fluoroelastomer like VPL with high fluorine content, or upgrade to even higher fluorine content, that is the perfluoroelastomer, where there is nothing else than carbon fluorine bonds.
Awesome. Thank you so much for answering that question. And of course, if there's any follow-up question, yeah, feel free to use that chat or Q&A feature. The next question for you, Nicola, is how can manufacturers ensure that these high-performance materials are used correctly and safely?
The best way is to have a dialogue all along the value chain, because in the elastomer industry, whatever the elastomer is always the same. We manufacturers sell the polymer to a compounder. That is the one that adds the vulcanization agents to the polymer. So we sell just this spaghetti. Then we need somebody that adds the ingredients to vulcanize them, some reinforcing filler like carbon black to give even more mechanical resistance. This compound that is ready to be vulcanized is usually passed to the next step of the value chain, that is the molder, the one that gives shape, that gives the form. The form is really the part, the rubber part. It can be an O-ring, a hose, whatever. And then this is installed in the equipment, be that a pump or an oil filter module, whatever. So the end of the value chain should follow all these steps to be sure that the polymer is the correct polymer is chosen, and it is in the polymer. The right polymer is a necessary condition to be safe in the application, but it is not sufficient, because you need also the right compounding ingredients, the right molding conditions. So it is key that all these parts, these players talk together. It's not easy, we know, but it is. The book says we should go like that. The more we talk in the value chain, the higher the probability of success.
Interesting. Thank you. Okay, it looks like we got one last question here. If no others come in, what other real-life examples can we provide of the successful use of fluoroelastomers in critical applications?
Many. I think of hoses, for example, now you know that recently we have all our cars have turbochargers to boost the performance and consuming less fuels. So these turbochargers have compressed air inside of very high temperatures, 200 degrees C or more, and there is also a circulation of the exhaust gases to minimize the pollution. So these hot gases including some traces of acid, of uncombusted oil. So the environment for the hose that drives the compressed air to the engine is very high. You need fluoroelastomers in the liner of that hose that are the only ones that can resist such environment. Without this kind of elastomer, without fluoroelastomer, probably the turbo charging technology would not exist. This is one of the most common application in the everyday life that I can think about.
Yeah, awesome. Thank you.
Another very quick was a failure in a flange or in the oil and gas industry. So there was crude oil passing through a pipe and leaking out of the pipe with very serious safety concerns, and we found out that the rubber was not the proper one. So we go back to the previous question: how can we ensure that the service is a safe service? In that case, the designer did not put the right rubber that was fluoroelastomer in contact with the crude oil, but he used a PDM, that everybody knows that is cheap, but because cheaper than fluoroelastomer, because also the performance is lower. So this causes chemical attack and failure of the pipe. So we had to suggest to design the flange with the real fluoroelastomer performing element.
Awesome. Wow. Thank you for providing those examples. Looks like we've answered all questions here. Thanks everyone for adding those questions to the Q&A feature. Thank you so much, Nicola, for coming on as a speaker, sharing your knowledge, and also I love your examples with the very Italian examples of the pasta and the coffee now. And I'm getting hungry. No.
Thank you, because also thanks to your articles, I mean, to the literature you provided to us, it was possible to deepen our knowledge about elastomers. So thank you also.
Amazing. Thank you so much. Have an amazing rest of your day, evening, everyone, and we'll be in touch. Bye.
Ciao.